Testing, testing. now I can advance the slide with this. Okay, where is the sensor for the
You just look at the.
sensor?
Yeah.
Where is the sensor? It doesn't matter.
I don't think it matters.
Okay.
As long as you point towards it, it should be great.
I don't think you can
Nah.
point anyway.
Try it? Yeah.
Yeah,
So it
it
doesn't.
doesn't matter.
Alright. So.
Is it on?
Yeah. Talk.
Are you sure? Is it on? Okay. Doesn't look like it's on.
No, it's because it's not a speaker. It's not a microphone. It's just for the calls.
Okay. No, I don't. I don't. Yeah. Sure, go ahead. I was joking moments ago that is it standing room only? Because I was expecting a larger audience, a bigger room.
Oh, a bigger room.
Yeah.
It's the biggest one in the building.
But I'll try to keep it light and simple and interesting. Because the crowd seems to be mostly students than faculty, so I think I'll sort of bring it down a notch or two to kind of draw them in, to get them interested in what we do, bring it down to day-to-day life where they see themselves making a difference and they can see themselves making that difference, rather than talking at that really detailed level where they keep wondering, how much more school do I need to attend before I can make a difference? Well, and there are people online as well, so I don't know how many are online. So in terms of the online crowd, is it mostly students like this or faculty and there's a mix?
Academia would be my guess.
Okay. Okay.
I mean, it's a YouTube channel,
Yeah.
right?
So we stream it on YouTube, and then it's a direct stream, and then once it's done, it gets uploaded on our YouTube channel.
Oh, really?
So we're trying to put all our seminars in there.
Ah, okay.
Okay.
All right.
Wow, perfect time. All right. It is my great pleasure to introduce the speaker today. As part of a delegation visiting us from
Thank you.
Idaho National Lab. So our speaker today is Dr. Gabriel Elevare, right?
Yes.
Gabriel is the manager of INL's Material Science and Engineering Department. He earned his bachelor's in industrial chemistry from Nigeria's University of Ibadan, and his PhD in material science and metallurgy at the University of Cambridge in the United Kingdom.
Right.
Before joining INL, he worked also in EPRI, and I think you spent time at Lawrence Livermore also?
Yeah, about almost 5 years at Lawrence
Among
Livermore.
many others, right?
Yeah.
As many stations along
Sure.
the way. He has over 20 years of experience in materials degradation management, surface reactions, and corrosion issues. And he's going to tell us everything we need to know about his department at INL.
Okay. Yeah. Thanks for the introduction. So contrary to what Yusri said, I am not going to be able to tell you everything about my department today. So when I looked at the, when Yusri sent us the agenda, I saw that he placed me at the end of the day. And there's a famous saying that no good deed goes unpunished. And so I have about almost 70 slides here to share with you. So if you have happy hour, I suggest you send a text and cancel happy hour, because we are going to be here for a long time. It's okay. Well, thanks for, I know you are all busy. It's the beginning of session. I know your time is precious. Let's make this fun. My department does a lot of things, and at INL, our DNA is in nuclear energy. That's our DNA. But we also do a lot of other things that are non-nuclear in nature. So what I've tried to do here is just to give you a flavor of what we do, snapshots, but a flavor. It's not everything. There are things I've left out, and I wish I hadn't left out. There are things I've included that that maybe you would like to hear less of. But let's make it fun. If you have a question, yeah, let's make it a discussion. You know, let's kind of learn from one another, okay, as we go along. And at close to 5, wherever we get to, I'll stop. And you know, how would you like to be able to ask questions for about 15 minutes? Okay, something like that. Okay, so I'll keep going until about 4:45, and wherever I get to at 4:45, I will stop and we'll ask questions. And if some of your questions, if I have slides for some of your questions, I'll go to those slides. Okay. So in the beginning, I'll go a little bit slowly. As I move on, I'll go a little bit faster. What I've tried to do, instead of just giving you capabilities, is to try to embed some of those capabilities that we have into ongoing programs, some of our large programs. I don't know how many of you know the history of the national labs, but there are 17 national labs in the country. And we are sort of loosely categorized by our missions. Okay. My first experience with national labs was Lawrence Livermore National Labs, and I worked there from 2001 to 2005. And my own idea of a national labs is everything under the sun should be possible in a national labs, right? It's a national labs. It's where everything that can't be done elsewhere is done in the United States. It's either nobody else can afford to do it, you know, that's where it's done. But as I have, you know, aged in the national lab system, I have come to find out that they are all mission-oriented. So loosely categorized into about 3. We have our science labs, the science-oriented fundamental science, and those are the ones at the top. That's where you find Argonne, SLAC, Oak Ridge. Those are the science labs. And then you have the energy labs. Their main mission is energy. NETL, INL, NREL, and Savannah River sort of does that a little bit, straddles. And then the third group are the weapons labs. Hell and destruction. That's, you know, you know, the entire weapons program. In fact, there's a particular secretary who didn't know that the nuclear arsenal rests in the Department of Energy. So all these labs are under the Department of Energy, not the Department of Defense, but the Department of Energy. Okay? So the entire weapons arsenal is managed under the Department of Energy by these 4 labs: Lawrence Livermore, Los Alamos, Sandia, and Savannah River. Okay? So in terms of Idaho National Labs, Idaho National Labs, I think, is the largest in terms of area of all the national labs. So we have our real estate is 890 square miles of real estate. Okay, so we are almost as large as the state of Rhode Island. Okay, not quite, almost as large. We have 177 miles of paved roads, 21 miles of railroads, 101 miles of electrical transmission and distribution lines. We have our own mass transit system. Okay, and all our buses run on bio-renewables and all that stuff. Buildings, almost 600. We have 3 fire stations, 3 reactors, down from over 50. We used to have over 50 reactors at Idaho National Labs throughout the life of the lab. Now we are down to 3. The most powerful research reactor, perhaps in the world, the ATR, is in INL. Okay? We have 2 spent fuel pools, 300 metric tons of used fuel, a lot of classified space, an explosive range, landfills. We have almost 5,000 employees. And in terms of business volume, we are a $1 billion enterprise. Okay? Right? So, everything we do tends to revolve around energy. Energy savings. That's what we do. We're an energies lab. So, when you look at the current grid, our current energy profile in this country, we generate electricity, wind, solar, thermal, nuclear. We put the electrons in the grid, and we send it to wherever it's going to be used. So this energy gets converted back into heat or whatever it is. Okay? That's our current paradigm. The paradigm of the future is that when we generate energy, we put more than electrons into the system. Okay? And if you need heat to drive a reaction in industry, why convert heat into electricity and back to heat? The energy that is lost in these conversions is so enormous that we can't afford to keep doing this. We will not survive. As an example, in 2015, we generate about 97.5 quads of energy, heat energy. Of that, we only are able to use 38.4 quads, which means we waste over 60% of the energy that we generate. And so there are these big ideas that we have today that have names like HEATR or nuclear reimagined that focus on figuring out how to generate, how to conserve the energy we generate. And in the ability, and in conserving that energy, we have to now start answering new questions. For instance, how do we bring down the level of heat that is wasted, the amount of heat that is wasted? What sort of materials would you have to conceive to be able to reduce energy loss by 10%, which is the whole idea that HEATR, the big idea HEATR runs on? Or in nuclear reimagined, how do you transport heat from a nuclear power industry, for instance, or a small modular reactor, or an advanced reactor, a thermal reactor, or a thermal generating plant, for instance, and get the heat from the plant to the site of where it's going to be used in industry? How do you do that? What sort of materials do you need? What sort of unidirectional heat transportation and heat conserving materials do you then need to start thinking up that are not even in existence today to be able to do that kind of thing? By 2050, our population will almost double, and if we keep wasting energy like this, we'll not be in a good place. Okay? So when you think about what INL does and how you can make a difference, not just with and for INL, but for the entire country and the world, you have to start thinking a little bit differently. Flexible generators, advanced processes, revolutionary designs, those are the things you have to start thinking about. And those are the things we think about on a daily basis. So, because we need to be a little bit more responsible with how we use energy, we have to start thinking about how to maximize these resources. So we are now demanding of our materials more, we are now demanding increasing physical, and we are now placing increasing physical and chemical demands on these materials so that we can generate energy at a higher density, so that we can satisfy our energy needs. Okay? And to meet these demands, we need to start thinking about different ways and fundamentals and better understanding materials fundamentals to be able to use these materials under extreme environments, extreme environmental conditions. And as we understand our materials and understand how to push them further, use them at higher temperatures, at higher pressures, we will start to do and improve in some areas. Our reactors, for instance, and our power plants will get smaller, and they will start generating as much or more energy than the larger ones of today. Higher temperatures, higher pressures. Advanced intelligent materials, materials that would heal themselves or resist these perturbations, okay, are some of the things we are thinking about. Advanced sensors. There are projects that we have today that work with sensors that go into fuel, that go into components, that will monitor real time what goes on in a reactor, for instance, or on a steam generator. And the engineer running the plant will be able to know exactly when that piece of equipment will break. We are not there today. We've started that process today. We've started looking at fundamentals in science and in engineering, and looking at advanced techniques to manufacture very low profile sensors, centimeters wide, microns high, microns wide, that we can co-print or co-manufacture into a component to use to monitor the health of the component. We'll be looking at smaller and higher density batteries, storage devices, and I'll give you some examples, some real life examples. They're not only smaller, they are higher density, meaning you'll be able to have a smaller energy pack in your computer. Instead of lasting 24 hours, you're looking at 48 or 72 hours. And they must cost less and have minimal impact on the environment. They must not damage the environment much more than the environment is being damaged today. Okay? And then if you look at your cars, we want to make them lighter, we want to make them more energy efficient. Because the fewer the number of, the higher the number of miles you can travel on a gallon of gas, the better it is for us. Okay? And reducing weight, we've done a lot of things with reducing the weight of cars, panels being thinner, but we have to do more. We now have to start designing materials that are even lighter and stronger than before. Our engines have to be smaller and operate at much higher temperatures in order to be able to generate more energy and increase the output from vehicles. Those are the things we need to think about today in order for our children and even for ourselves when we are gray, to be able to survive and to be able to afford to live in a country like this. Okay? So a lot of what we are doing is putting materials in extreme environments. And for a lot of you who are savvy in the nuclear industry or in the energy industry, when you think about extreme environments, you're thinking about high stress levels, high strain levels, high temperatures, high pressure. So this is, how many of you know about Davis-Besse? Okay, Davis-Besse nuclear plant. Okay, so this is from Davis-Besse. So that is a reactor pressure vessel head. Okay, the penetration of the penetration that the control rod drives that lower the control rod blades that drive down the nuclear the fission reaction by absorbing neutrons cracked. Okay, boric acid leaked out onto mild steel. Inside of the reactor is stainless steel, 1/4 inch stainless steel. Okay, on the inside. The shell of the reactor itself is 9 inches thick. Okay, had a crack, leaked out, and created that hole, the size of a football. The only thing that prevented a local loss of coolant accident that caused the reactor to melt down is 1/4 inch, about 5 millimeters stainless steel. And on the cladding, some of the cracks on the cladding were 75% through wall. So the only thing that stood between us and a catastrophic accident in Davis-Besse was 25% of 1/4 of an inch. So about 1.5 millimeters. Okay. That is fuel, gases, irradiation, cause that really nice pattern. While it looks nice for all sorts of designs, not good for energy. That is a solar collecting panel for concentrating solar power. All these mirrors are on a gimbal, shines up here. This can go up to about 550 degrees Celsius. Now we are in Gen 3, and Gen 3 is upwards of 700 degrees Celsius. How do you create materials that can do this and do this consistently every day? And when the sun rises and then sets at night, your temperature variation could be over 200 degrees Celsius. And you do that every day for years on end. How do we do this? We are building larger and taller windmills. And when they get to a certain size, structurally they are not sound, wind gusts, they fall. So these are some of the things that people think about, and people are exactly in the energy industry. But when you come back home, when you think about, okay, how does this touch me? Okay, maybe nuclear power reactors, that's not my thing. But how does this touch me every day? Okay. Any of you own hoverboards? No? Okay, all right. So, all right, but you know that hoverboards were banned from aircrafts, okay? And the reason why they were banned from aircraft is that they started combusting, all right? Those hoverboards and the conditions in those hoverboards were subjected to extreme environments for the materials, and the materials failed. We've all flown, right? Okay? Boeing 787. See this part right here? Lithium-ion batteries. Okay? Spontaneous combustion. Okay? That touches you, right? How many of you own Samsung phones? Samsung? Okay. How many of you know about the Note 7 Samsung phone? I owned one, I had to return it. That's a Note 7. That's the battery. Okay, you charge it, it burns. Now, why? These things need a lot of energy. And you want to make them small because nobody will put a phone in a backpack. All right? You want to put it in your pocket. You want to put it on your, tights. Small, compact, high density, high energy. If you miss the architecture, you cause something that is catastrophic. So what is an extreme environment? An extreme environment is any environment that causes a material to malfunction or not to function to design specifications when you subject it to that environment. Ordinary drinking water could be an extreme environment if you must use sodium metal. Okay? If you must use sodium metal, ordinary water is an extreme environment because your sodium will explode. Right? So when you think about extreme environments, don't think about just high temperature, high pressure. Think about what do I need to use? Where do I need to use it? What will happen if I get it wrong? So some of these environments were inadvertently created through lack of understanding. All right? Like architectures, for instance. And so the goal here is to improve the understanding of all these materials to expand the safety operating envelope of these materials far beyond what we currently use now to be able to satisfy all our energy requirements now and in the future. So when you think about materials, whether nuclear or solar or otherwise, these are the things you need to be thinking about. And these are the this is our thought pattern and our perspective at INL. Okay. Any questions so far? No? Okay. So, I've gone through this. So, we really need to start thinking about different ways of reliably generating electricity for the future. And some of the things we need to start thinking about, okay, are all these things, but from a materials perspective, revolutionary concepts in materials design, and advanced manufacturing and enabling technologies. Okay? So some of the things we manufacture now, the way we manufacture them now, will not be amenable to the way we manufacture the components and the materials of the future. Right? So, kind of do things. Atomic structures and complex property definitions, which helps us to develop from first principle multi-scale description of the complex properties that our materials must have in order for us to get what we want. Then we use our advanced modeling and simulations tools to design novel materials to meet those needs that we have defined from down to the atomistic structures. And then in order to increase fundamental understanding of this, R&D, we characterize the material, we test the material surface reactions, mechanical resilience, chemical resilience, and simulations to validate the safety operating envelope of these materials. Then you fabricate and you deploy. And hopefully we get it right, and we have a material that has demonstrated resilience for any extreme environment you put it through. Hopefully it does not take us 25 years. Because if you look at the nuclear power reactors of today, a new material takes about 20 to 25 years to get from concept to deployment. Alloy 690 is a good example, a replacement for alloy 600. They were testing alloy 690 before I joined EPRI. They are still testing alloy 690 after I've left the company, and they'll keep on testing it for a while. You don't want to do that. We want to shrink the 20 years down to 5 years. For that, we need your brains. These brains, there's a lot of mileage on it. Yours, they're like Ferraris. You know, we need those, okay? Right. Now, when you're thinking about materials development, materials deployment, or materials redeployment, there are three things you have to keep in mind. The first thing we look at is, are there any materials currently that we have that can satisfy these needs? Okay? So we'll always look for current materials. Okay? We repurpose materials. So for instance, alloy 617 has been redeployed for advanced gas reactors that can operate at 950 degrees Celsius. They weren't originally designed for that. It saves time, it saves money, and usually there's a lot of data from the qualification of the material, so you don't have to start from scratch. Now, if there is no material that can satisfy a need, what we look at first is, okay, can we change something in that current material to improve the properties? Bump up the amount of molybdenum, for instance, that we have in alloy 600, double the amount of chrome, bump up the amount of moly, 600 becomes 690. And suddenly, new material, right? And we grandfathered all the tests and qualifications from 600 to 690. We repeat it or not, it didn't matter. We just transferred everything over. And slowly but surely, like your colleagues in CEA, in SACLE, in EDF, in Arriva, they started figuring out that, you know what, maybe we don't need to heat treat for 12 and a half hours, maybe 5 hours are enough, because there's so much chromium, it solutions faster, right? And when that fails, then you start thinking about new materials. And whatever new materials you come up with, there's a cost, you must be cost conscious. If your material costs $1 million a pound, it's not going to be useful to anybody. It's going to be unobtainium like on Avatar. Okay? So that's the slow part, okay? So I'll quickly go over some projects we are running, some capabilities, wrap around those, and I'll kind of go fairly quickly. So if you need to stop me, stop me. I have 1, 2, 3, 4, maybe 20 minutes, okay? Right? So, advanced reactor technologies. To this group, this is you, okay? So the goal here is to provide the technical basis to support regulatory requirements for structural materials that are required for advanced reactors, and I'll give you a flavor of that. So, and as part of that, we are developing ASME, boiler, and PVP codes that are mandatory requirements to be able to deploy these materials in the field. So our ATR focuses on fast, gas-cooled, and other very high-temperature reactors. When I mean very high-temperature reactors, we are approaching 1,000 degrees Celsius, and I'll give you a reference point from that. Material 617, 800, 709 graphite. All these are used in gas-cooled reactors with the exception of 709 that is going to be deployed in a fast reactor. Okay? Is that slow enough? Okay, so gas-cooled. So currently, some of our hottest operating reactors are light water reactors, PWRs. Hottest part of a PWR is in the pressurizer, 345 degrees Celsius. Above that is trouble. Life is anything from before things start breaking, maybe 10 years, and if we push it far enough, maybe 40 years. Okay. Now, we decided that, well, we haven't solved all the problems at 300 degrees Celsius. We're going to complicate our problems further. We now decided that 760 is where we are going to start. And we have to last for 300,000 hours. Okay, simple enough. And then we decided that, okay, there's an intermediate heat exchanger that we have to put into the system. And this IHX runs at 950 degrees Celsius, and it has to last for 20 years. What the hell are we thinking about? We haven't solved all the problems at 300 degrees Celsius. We are thinking, you know what? Let's leave that alone and let's take on the 1,000 degrees Celsius problems. That's why we need you. Okay? So we are good with creating the problems. You have to solve those problems. And so, baseline properties, mechanical strength, tensile strength, creep fatigue, blah, blah, blah. Think about everything. We have to do all that. Materials degradation mechanisms, prediction models to boot, because we must be able to predict how the reactor would operate for the next 20 years before we flick the switch. At least that is the ideal, although we have never succeeded in doing that. Then we have to write code cases and standards for deployment. Simple, right? Okay. So we've been working on this now for over a dozen years. We continue to work on it. And your group, please let us know how we can help. Guys, let me know how we can help you.
What's the so sensitive about this 371 degrees Celsius?
What?
What is so sensitive about 371 degrees Celsius?
Well, the 371 degrees Celsius is the code qualification for weldability. 372, well, maybe we don't care that much. No, I don't know. I am not, see, I am the head of department, but I have 30 plus very smart people working with me, and so I don't have to think about every single number in the book. All right? So big picture, that's me. Little picture, no. Okay? Anyway, but I'll get that for you. Okay? Right. So in terms of the equipment we deploy, at the time I originally put this slide together, we had a total of 47 load frames, okay, that can do all sorts of things, from electromechanical to servo hydraulic, creep frames, creep fatigue. We actually even built 2 stress relaxation frames. We bought it from ATS. They didn't meet our specs. Our folks tore it down, put it back together, much better than ATS actually. So they will have to pay us to get those systems and the designs from us. We also have a Gleeble. Okay, so these gleebles can do tensile torsion and variants of those. We can use them for weld simulations. And one of the cool things about a gleeble is it's very fast in terms of fast analysis, and you can heat up a specimen at a rate of 1,000 degrees per second that will simulate welds. Okay, and when you apply modeling and simulation tools like DFT, it's very, very powerful. Some of our chambers are temperature controlled, like this one and that one. And we have these Agilent systems, these gas chromatographs, that are able to deliver ppm accuracy in gaseous substances into these chambers to simulate certain environments. Okay, to be able to do all this. So I'm kind of just showing you all this so that you know what sort of resources are available to you through INL to be able to, you know, help us out with some of the problems, some of the very simple problems I've just outlined. Okay. Some of our specimens for 17 multi-axial, weakening strength, creep deformation. So these are some of the specimens we use, some of the profiles that come from these specimens. We have a graphite program. Now, the core and the fuel, where the fuel rests and the reflector blocks of some of these gas-cooled reactors is graphite, made of graphite blocks. Problem number one. All the really brilliant guys who used to manufacture graphite all died off. No, not really. So actually, graphite itself is, the manufacture of graphite itself is a science as much as an art. Okay? And so batch to batch of graphite might not give you the same functionality, the same response to perturbations, the same performance. So this program, recognizing that, wants to create a set of standards to be used to grade graphite more accurately as we are going to be applying them in some of our advanced reactors. And so this entire suite, materials behavior, baseline properties, irradiation behavior, mechanical analysis, feed into defining the safe working envelope for neutron graphite and protection of fuel. That's all you need to know for now, okay? And so to support this effort, well, of course, NRC and ASME got involved. They said it was necessary. Many of the graphite reactors around the world have limited data, so we have to generate new data, a lot of sleepless nights and the whole 9 yards, and there we go, gas-cooled reactors all over the place. So we have a whole carbon characterization lab to support this effort. We can do materials properties, irradiated and non-irradiated carbon materials properties, high temperature testing, including irradiation, annealing studies, and oxidation degradation. Because graphite doesn't activate when you irradiate it, we can irradiate it in our ATR in the desert and bring it to our facilities in town, and we all don't glow in the dark after we work with graphite. So that's a really good thing. But one of the things that is really important is this NQA1 quality. That is Nuclear Quality Assurance Class 1. Extremely important. If you don't have NQA1, you can put it in a nuclear reactor in this country. Okay? So we deploy all sorts of techniques, ND techniques, X-ray CT tomography, Raman. A lot of our studies are performed at higher than 2,500 degrees Celsius. This furnace, for instance, which looks like one that I saw in one of your labs, functions at 2,800 degrees Celsius. So some of the things we do and some of the things we can deploy. This is a fuel pellet with trisoparticles, and this trisoparticle has fissile material in it and about two or three layers covering that fissile material. And then you press it into a carbon matrix. And sometimes when you deploy the fuel, it cracks. It does all sorts of funny things. You want to know how it behaves. X-ray CT tomography, you can do amazing things. Okay, that's the block. You can isolate. You can strip out from subtraction. You can strip out all the binding material. You can strip out, and you want to see just the trisoparticles. You can even isolate just the cracks. If you want to see where the cracks went, you can remove everything else and just view the cracks. And view the cracks in relation to the trisoparticles or to the binder. And so you can more accurately analyze performance of the fuel. Okay? Modeling and simulations is very big for oxidation, fracture, radiation damage, increased energy storage, and chemical reactivity, both in the gaseous and the liquid phases when we are looking at our fuels. Okay? Concentrating solar power. Any questions? No? Okay. So concentrating solar power. I showed you that solar collecting tower, glowing white hot, 550 something degrees Celsius, day, night, and the whole 9 yards. Now, one thing about concentrating solar power is that because the sun doesn't shine at night, you need to be able to capture that energy, put it into something, and conserve it overnight so that you keep your grid going. And so you need molten salt. Okay, so these molten salts are deployed not only in concentrating solar power, they are also deployed with molten salt reactors as well as the coolant, okay, the thermal fluid. Now, so there are few solar concentrated CSP plants deployed around the world. And so some people in DOE got together and said, you know what, let's forget about, well, maybe let's forget a little bit about some of the problems that we are still trying to solve. Let's actually increase your problems. So let's go from Gen 2, that tops at about 560 degrees Celsius, and let's move on to Gen 3. And the reason we want to move on to Gen 3 is higher energy densities. We need to produce more energy, smaller footprint, faster than we are able to produce it now. So we'll jack up the temperature to over 700 degrees Celsius. So they put out the call. Some of my engineers and scientists answered the call, and we won one of the grants. And so what we are looking at now is the creep fatigue properties of materials going to be used for concentrating solar power at operating temperatures in excess of 700 degrees Celsius. Something very similar is another project that is not on here right now that I did not include, but I think it's important for me to mention. Extreme environment materials for fossil energy generation using ultra supercritical CO2 as the coolant. Again, the really critical thing about that project, and we are involved with 6 other national labs running this project. It used to be a big idea that didn't make it, but somebody still liked it and championed it, is that 700 degrees Celsius plus starts to come up. And so in this situation, coolant is ultra supercritical CO2 to be able to use that to turn turbines, okay? And so now you are starting to see a pattern. We need to generate energy at higher densities, which means we have to go to higher temperatures, which means the materials we are using today at 300 and we are having problems with them, we'll have to step our game up. Okay? You think I can do that by myself? We need all of you to help us out to do that. So, one other problem, so Gen 2 550, Gen 3 700. So now with all the increased temperatures, there's also another problem. When the sun sets, okay, temperatures drop, and those temperatures can drop by as much as 200 degrees Celsius. And you do that every day. And you're expected, and with the initial capital outlay, you are expected to keep doing that every single day for over 20 years. Heat, cool, heat, cool. Sometimes the heating and cooling cycle takes place during the day because when we have cloud cover, temperature drops. When clouds go away, temperature rises, so you can have several cycles during the day. What does that do to your material? It fatigues the living daylights out of it. And while you are fatiguing the material, because you are operating at high temperature, you creep the thing up. So how do you manage that? That's one of the things we are trying to do. Okay? Advanced manufacturing. Additive manufacturing. We've heard of additive manufacturing? Anybody? Additive? So what do you like about additive manufacturing? You can make anything. Have you tried to make anything? What do you like about additive manufacturing?
It can realize
Some
some dreams.
dreams. How about just one? For starters. Okay. So both of you are right. So when the harbingers, when the folks, the avant-garde of additive manufacturing burst onto the scene, they said, you know, guys, in the past, you go to the mine, pickaxe, then shovels, then bulldozers. crush stuff, smelt stuff, roll it in the mill. You have a hunk of metal, you check whether the microstructure is okay. If you are okay, then you get all these machines and start machining parts out, right? And you carve parts out, okay? Subtractive manufacturing, right? Yeah, that's 15th century, right? So what we're going to do is we're going to take that same material, make it into powder form or wire form, pump it into this machine, connect it to a computer just like your printer, and voila, we can print anything, right? Okay. See, what they didn't tell you is that all those processes, from the mining of the ore to the chemical beneficiation to the smelt